The terraforming of Venus is the theoretical process of engineering the global environment of the planet Venus in such a way as to make it suitable for human habitation. Terraforming Venus was first seriously proposed by the astronomer Carl Sagan in 1961, although fictional treatments, such as The Big Rain by Poul Anderson, preceded it. The minimum adjustments to the existing environment of Venus to support human life would require three major changes to the planet. These three changes are closely interrelated, because Venus's extreme temperature is due to the greenhouse effect caused by its dense carbon dioxide atmosphere, reducing Venus's surface temperature of 462 degrees Celsius. Eliminating most of the planet's dense 9.2 per carbon dioxide and sulfur dioxide atmosphere, via removal or conversion to some other form. Addition of breathable oxygen to the atmosphere. Solar shades. Venus receives about twice the sunlight that Earth does, which is thought to have contributed to its runaway greenhouse effect. Terraforming Venus would probably involve reducing the insulation at Venus's surface to prevent the planet from heating up again. Space-based equals, solar shades could be used to reduce the total insulation received by Venus, cooling the planet somewhat. A shade placed in the Sune-Venus L1 Lagrangian point also serves to block the solar wind, removing the radiation exposure problem on Venus. Construction of a suitably large solar shade is a daunting task. The size of the shade would be 4 times the diameter of Venus itself if at the L1 point. This size would necessitate construction in space. There would also be the difficulty of balancing a thin film shade perpendicular to the Sun's rays at the Sune-Venus Lagrangian point with the incoming radiation pressure, which would tend to turn the shade into a huge solar sail. If the shade were left at the L1 point, the pressure would add force to the sunward side and necessitate moving the shade even closer to the Sun than the L1 point. Modifications to the L1 solar shade design have been suggested to solve the solar sail problem. One suggested method is to use polar orbiting, solar synchronous mirrors that reflect light toward the back of the Sun shade, from the non-sunward side of Venus. Photon pressure would push the support mirrors to an angle of 30 degrees away from the sunward side. Paul Birch proposed a slatted system of mirrors near the L1 point between Venus and the Sun. The shade's panels would not be perpendicular to the Sun's rays, but instead at an angle of 30 degrees, such that the reflected light would strike the next panel, negating the photon pressure. Each successive row of panels would be +/1 degree off the 30-degree deflection angle, causing the reflected light to be skewed 4 degrees from striking Venus. Solar shades could also serve as solar power generators. Space-based solar shade techniques, and thin-film solar sails in general, are only in an early stage of development. The vast sizes require a quantity of material that is many orders of magnitude greater than any human-made object that has ever been brought into space or constructed in space. Atmospheric or surface-based equals. Cooling could also be affected by placing reflectors in the atmosphere or on the surface. Reflective balloons floating in the upper atmosphere could create shade. The number and/or size of the balloons would necessarily be great. Jeffrey A. Landis has suggested that if enough floating cities were built, they could form a solar shield around the planet, and could simultaneously be used to process the atmosphere into a more desirable form, thus combining the solar shield theory and the atmospheric processing theory with a scalable technology that would immediately provide living space in the Venusian atmosphere. If made from carbon nanotubes or graphene, then the major structural materials can be produced using carbon dioxide gathered in situ from the atmosphere. The recently synthesized amorphous carbonia might prove a useful structural material if it can be quenched to STP conditions, perhaps in a mixture with regular silica glass. According to Birch's analysis, such colonies and materials would provide an immediate economic return from colonizing Venus, funding further terraforming efforts. Increasing the planet's albedo by deploying light color or reflective material on the surface could help keep the atmosphere cool. The amount would be large and would have to be put in place after the atmosphere had been modified already, because Venus's surface is currently completely shrouded by clouds. An advantage of atmospheric and surface cooling solutions is that they take advantage of existing technology. A disadvantage is that Venus already has highly reflective clouds, so any approach would have to significantly surpass this to make a difference. Eliminating the dense carbon dioxide atmosphere. Biological approaches A method proposed in 1961 by Carl Sagan involves the use of genetically engineered bacteria to fix carbon into organic forms. Although this method is still commonly proposed in discussions of Venus terraforming, later discoveries showed it would not be successful. The production of organic molecules from carbon dioxide requires an input of hydrogen, which on Earth is taken from its abundant supply of water, but which is nearly non-existent on Venus. Because Venus lacks a magnetic field, the upper atmosphere is exposed to direct erosion by solar wind and has lost most of its original hydrogen to space. Furthermore, any carbon that was bound up in organic molecules would quickly be converted to carbon dioxide again by the hot surface environment. Venus would not begin to cool down until after most of the carbon dioxide has already been removed. 33 years later, in Pale Blue Dot, Sagan conceded that his original proposal for terraforming would not work because the atmosphere of Venus is far denser than was known in 1961. Floating colonies could gradually transform the Venusian atmosphere. For example, their reflectivity could alter the overall albedo of Venus. Colonies could also grow plant matter, if water or another source of hydrogen were imported, which would gradually sequester carbon dioxide in the air. However, it would take an enormous number of such colonies, and large quantities of introduced hydrogen, to have a significant atmospheric impact, because there is over 1.2 1020 kilograms of carbon in Venus's atmosphere. Introduction of hydrogen according to Birch, bombarding Venus with hydrogen and reacting it with carbon dioxide, could produce elemental carbon and water by the Bosch reaction. It would take about 1019 kilograms of hydrogen to convert the whole Venerian atmosphere, and such a large amount of hydrogen could be obtained from the gas giants or their moon's ice. Iron aerosol in the atmosphere will also be required for the reaction to work, and iron can come from Mercury, asteroids, or the Moon. Due to the relatively flat surface, this water would cover about 80% of the surface, compared to 70% for Earth, even though it would amount to only roughly 10% of the water found on Earth. The remaining atmosphere, at around 3 bars, will mainly be composed of nitrogen, some of which will dissolve into the new oceans of water, reducing atmospheric pressure further, in accordance with Henry's law. Capturing carbonates bombardment of Venus with refined magnesium and calcium could sequester carbon dioxide in the form of calcium and magnesium carbonates. About 1020 kilograms of calcium or 1020 kilograms of magnesium would be required, which would entail a great deal of mining and mineral refining. 1020 kilograms is a few times the mass of the asteroid 4 Vesta in diameter. Modeling by Mark Bullock of Venus's atmospheric evolution suggests that existing surface minerals, particularly calcium and magnesium oxides, could serve as a sink of carbon dioxide and sulfur dioxide. If these could be exposed to the atmosphere, then the planet would cool and its atmospheric pressure decline somewhat. One of the possible end states modeled by Bullock was a 43-bar atmosphere and 400 Kelvin surface temperature. Direct liquefaction and sequestration Birch's proposal involves using a solar shade to cool Venus down sufficiently to permit liquefaction, from a temperature less than 304.18 kelvins and partial pressures of CO2 down to 73.8 bar and then down to 5.185 bar and 216.85 kelvins. Below that temperature, freezing of atmospheric carbon dioxide into dry ice will cause it to deposit onto the surface, after which the frozen CO2 would be buried and maintained in that condition by pressure, or shipped off-world. After this process was complete, the shades could be removed or soletas added, allowing the planet to partially warm again to temperatures comfortable for Earth life. A source of hydrogen or water would still be needed, and some of the remaining 3.5 bar of atmospheric nitrogen would need to be fixed in the soil. Birch suggests disrupting an icy moon of Saturn and bombarding Venus with its fragments to provide perhaps an average depth of 100 meters of water over the whole planet. Removing atmosphere equals, the removal of Venus's atmosphere could be attempted by a variety of methods, possibly in combination. Directly lifting atmospheric gas from Venus into space would probably prove difficult. Venus has sufficiently high escape velocity to make blasting it away with asteroid impacts impractical. Poul and Sagan calculated in 1994 that an impactor of 700 km diameter striking Venus at greater than 20 km per second, would eject all the atmosphere above the horizon as seen from the point of impact, but because this is less than a thousandth of the total atmosphere and there would be diminishing returns as the atmosphere's density decreases, a very great number of such giant impactors would be required. Landis calculated that to lower the pressure from 92 bar to 1 bar would require a minimum of 2,000 impacts, even if the efficiency of atmosphere removal was perfect. Smaller objects would not work either, because more would be required. The violence of the bombardment could well result in significant outgassing that would replace removed atmosphere. Most of the ejected atmosphere would go into solar orbit near Venus, and, without further intervention, could be captured by Venus's gravitational field and become part of the atmosphere once again. Removal of atmospheric gas in a more controlled manner could also prove difficult. Venus's extremely slow rotation means that space elevators would be very difficult to construct because the planet's geostationary orbit lies an impractical distance above the surface. And the very thick atmosphere to be removed makes mass drivers useless for removing payloads from the planet's surface. Possible workarounds include placing mass drivers on high-altitude balloons or balloon-supported towers extending above the bulk of the atmosphere, using space fountains, or rotavators. In addition, if the density of the atmosphere were dramatically reduced, the surface temperature would probably vary widely between dayside and nightside. Another side effect to atmospheric density reduction could be the creation of zones of dramatic weather activity or storms at the terminator because large volumes of atmosphere underwent rapid heating or cooling. Day-night cycle, Venus rotates once every 243 days by far the slowest rotation period of any of the major planets. A Venerian sidereal day thus lasts more than a Venerian year. However, the length of a solar day on Venus is significantly shorter than the sidereal day. To an observer on the surface of Venus, the time from one sunrise to the next would be 116.75 days. Nevertheless, Venus's extremely slow rotation rate would result in extremely long days and nights, which could prove difficult for most known Earth species of plants and animals to adapt to. The slow rotation also probably accounts for the lack of a significant magnetic field. Space mirrors equals, one proposal to compensate for the rotation rate is a system of orbiting solar mirrors which might be used to provide sunlight to the night side of Venus and possibly shade to the dayside surface. In addition to his suggestion of slatted system of mirrors near the L1 point between Venus and the Sun, Paul has proposed a rotating Soletta mirror in a polar orbit, which would produce a 24-hour light cycle. Changing rotation speed equals, increasing the speed of Venus's rotation would require energy many orders of magnitude greater than the construction of orbiting solar mirrors, or even than the removal of Venus's atmosphere. Recent scientific research suggests that close flybys of asteroids or cometary bodies larger than 60 miles across could be used to move a planet in its orbit, or increase the speed of rotation. G. David Nordley has suggested, in fiction, that Venus might be spun up to a day length of 30 Earth days by exporting the atmosphere of Venus into space via mass drivers. A proposal by Birch involves the use of dynamic compression members to transfer energy and momentum via high-velocity mass streams to a band around the equator of Venus. He calculated that this would give Venus a day of 24 hours in 30 years. See also, terraforming, colonization of Venus, terraforming of Mars, terraforming of Europa. References. External links, Visualizing the Steps of Solar System Terraforming, a fictional account of the terraformation of Venus, Terraform Venus, Terraforming Venus, The Latest Thinking.